And I'm live. That is cool. Today is 25th of August 2025, Monday, and we are going to continue our dynamic programming thingy. Yesterday we were doing knapsack. We are going to continue that knapsack from Competitive Programmers Handbook, dynamic programming section, this thing. And we did write a function for this thing, and we actually wrote function for this and for this, but this to me is not very clear just yet. So we have to do some more practice on this on knapsack, and well, eventually on the other parts. There are only two things remaining: edit distance and counting tiles. Okay, so we can either continue with knapsack right now and then go to these two other remaining things, or what I'm thinking is we can just first go through these two things and then the CPL algorithms. Yep. And then we can go through the whole dynamic programming section of CP algorithms. Yep. Introduction to dynamic programming. Then there is knapsack, a whole article on knapsack, zero knapsack, and there is nothing on zero infinity knapsack. Then there is DP optimization, divide and conquer. That is cool. And then there is Knuth optimization. Knuth's optimization. Knuth is a Donald Knuth is a really nice guy. He is very old, by the way. I think he was born in 1938, which is ancient. 1938, 1938. Yes, he is ancient. And then there is tasks. Dynamic programming on broken profile problem. Parkit, Parkit. Finding the largest is zero submatrix. Okay, we will have to go into these two things. But yeah, so first we will complete these two remaining things, and complete in the sense gloss over these two things, at least get an understanding of what these means, and then read articles on CP algorithms and do some CACS, dynamic programming problems. At least maybe a problem like this might be very hard because there are only 4,000 attempts and only 2,000 people have been able to do these. But the other ones, like till this point, I think we should be able to do them after we have read some things. Yeah, for a couple of days, maybe even a week, everything would be dynamic programming related, and that is cool. We can go from topic to topic, and that is very, very cool. And yesterday was also a contest, and yesterday's contest was pretty good. I was able to do two questions. I figured out how to do the third question, but submission messed up in some way. Y- Yep, I did two questions, and the third one, I figured out a very elegant way to do this one, but maybe something because of interactive, some technical thing messed up, and yeah, my pretest gave wrong answer on two. My solution gave wrong answer on pretest two, which is bad. So yeah, let's move on to edit distance. But before moving on to that, I would like to summarize what knapsack problems are. In knapsack problems, we have been given, well, the version that they in this article is presented is that given a set of numbers, what are the possible sums that we could reach using different configurations. So if we have numbers like 1, 3, 3, 5, then we can have a sum of 0, 1, 3, 4, 5, 6, 9, 11, 12, and that is cool. And how we do this is we ask this: for every sum, we start iterating from 0 till the maximum possible sum, which is the sum when you are taking all of the elements. So you ask for every number in between these two numbers and also including these two numbers, is this sum possible? For one, you ask, is the sum possible? And how you ask it is the sum of one possible when you are considering all of these elements? And then you remove one of the elements, let's say the last one, and then you ask two questions. Is the sum of one possible when I didn't use the fifth element? And is the sum of now -4 possible when you did use the fifth element to get to 1? And you just keep repeating that until your set goes down to 0. And if the sum that you want with a empty set equals 0, then you would be able to get a sum of 1 with the set that you began with. And you do this for every single number in your list from 0 till the maximum possible sum. And that is cool. And they have written there is this tabular representation, and dynamic programming in general is a tabular method. And the word dynamic was given to it by the creator of dynamic programming, and there was a reason for that. I forgot. The reason was that maybe where he was working, the place that he was working at, it was more supportive for programming things. Therefore, he used the name dynamic programming. But instead, what this means actually, dynamic programming means tabular representation of data in which you reuse stuff. Like, yeah, and yeah, we used a matrix first to store the state, and then we used a single array in which we store the state. And yeah, that were the two programs that we wrote in knapsack yesterday. And without a full understanding of knapsack, without practicing anymore, we will move on to the next topic, which are like only two: edit, distance, and the next one, counting tiles. We will continue them, read about them, and then go to CP algorithms, read some stuff there, and then go to CSES and solve some problems. That is going to be cool. Hello, do not call me sir. That is not very cool. I'm just learning with the camera on. Yep, edit distance. The edit distance or Levenstein distance is the minimum number of editing operations needed to transform a string into another string. The allowed editing operations are as follows: insert a character, remove a character, modify a character. Okay. And edit distance or Leventish distance. Given a string, I want to convert that string into another string. Okay, and I can insert a character into my starting string. I can remove a character from my starting string, or I can modify a character from my starting string. So, for example, the edit distance between love and movie would be, I can change this L into a M. I would have MOVE, and then I can insert I. I will get stuff. I will get movie. So 2 is correct, because we can first perform the operation this love to move, modify, and then operation move to movie, insert. This is the smallest possible number of operations, because it is clear that only one operation is not enough, because the length is here 4 and the length here is 5, but you also need to change this L. So at least 2 operations, and these were the 2 operations. Change L to M and then insert I. Suppose that we are given a string X of length N and a string Y of length M, and we want to calculate the edit distance between X and Y. To solve the problem, we define our function distance AB that gives the edit distance between prefixes. That makes sense. That makes sense. That makes sense. We can, okay, we define a function AB that gives the edit distance between prefixes in X and prefix in Y. prefix in x from 0 to a and prefix in y from 0 to b. Thus, using this function, the edit distance between x and y equals distance n minus 1 and m minus 1. Okay, why do we have n and m? N is the length of x, makes sense, and m is the length of y. Using this function, the edited distance between x and y is equals distance this. Okay, we can call the function on this thing, and now we only have to define a recurrence behavior for this function for distance ab, this thing. Okay, we can calculate the values of distances as follows. Distance ab is the minimum distance between distance a b minus 1 plus 1. Okay, you removed one thing from b, and that is one operation. You removed one thing from a, that is one operation. And distance a, you removed one thing from both, and plus cost eb. What is cost eb? Here cost eb equals 0. Was there a function named cost? No. Nope. Here cost ab equals 0 if xa equals yb. Makes sense. Makes sense. And otherwise cost ab equals 1 if they are not equal, if I have to modify one of them, or like a, because a is the thing that we are trying to convert into b. The formula considers the following ways to edit the string x. Okay, we will not look at that. We will look at this and we will try to figure out what these things are trying to do. And here we have distance a and b minus 1. To calculate distance ab, a is a index in the string x, b is an index in the string y, and this thing gives us the edit distance between the prefix 0 to a and the prefix 0 to b in x and y respectively. And to calculate distance ab, we have a recursive formula somehow. We need the minimum cost between these. Okay, we have a few operations. We could insert, we could remove, or we could modify a character. Okay, if we do this, minimum of a and b minus 1 plus 1, what does this thing do? This thing removes one thing from b, and that increases one amount of operation. To get back to the length a and b, you would have to do one more operation. And distance, and if you were to remove one character from a, from the end of a, and then to get back to the original length a, you would have to do one more operation. But a and b are also not guaranteed to be equal. A and b could be any length, so that is also crazy. Distance a minus b, you remove one character from a and one from b respectively from both of the things. And and then you add the cost of a and b. Cost of a and b is 1 if a and b, eighth and bth characters are different, and it is 0 if they are same. Okay, here cost equals 0 if they are same and equals 1 if they are different. Okay, distance a to b minus 1, insert a character at the end of x. X is a, insert a character at the end of x. This remove the last character from x. That makes so much sense because we are not doing any operation thing on y, we are only performing operations on x. Therefore, when this thing happens, when we reduce the size of the target string, we cannot do that. We cannot do that. So this is equivalent to adding some character to a, to our original x string. That makes sense. And when we are removing, we can actually remove the last character from it. And when we are doing this, because this is accompanied, this would be like This is equivalent to modifying, match or modify the last character of X. Makes sense. So we have used insertion, we have used removal, and also modification. So we have used all the three possible operations, and we are seeing which one gives the minimum thing. That makes sense. And we are starting from the end, from the prefix, from the end. Okay. Okay. In the two first cases, one editing operation is needed, insert or remove. In the first two cases, one editing operation is needed, insertion or removal. In the last case, this thing, if they are equal, we can match the last character without editing, and otherwise, one editing. Yes, that makes so much sense. If the last characters are equal, then we can just skip that part and go to a lower prefix. That makes sense. We can match the last characters without editing, and otherwise one editing operation is needed if they are not equal. And whatever is the minimum thing, we perform that. But we need to look at this at a meta level somehow, so that we know what is the meta level idea behind this thing. The following table is the main thing in dynamic programming. The distance is named after VI Levinstein, who studied it in connection with binary codes. Okay, movie and love. Okay, we have this thing, and this is the edit distance. Okay, when we are considering the subset of L and M, we just do one edit operation, and we have this. And when we are considering L with MO, we can convert L into something and insert one more character, and the same for rest of the thing. Then if we start with LO and we want to convert it into M, then we can convert L or O into M and remove the other remaining character. And when MO, we do not have to convert O, it is already present. We just convert L into M, and at the end, answer is this 2. Okay, that somehow makes sense. The lower right corner of the triangle tells us that the edit distance between love and movie is 2. The table also shows how to construct the shortest sequence of editing operations. In this case, the path is as follows. We start from here and go there. Okay, I guess this must mean something. Why we are traversing this grid? The last character of love and movie are equal, so the edit distance between them equals the edit distance between LOV and MOVI. Yep, E and E are same, so 2 and 2 makes sense. We can use one editing operation to remove the character I from movie. Thus, the editing distance N1 is one larger than the edit distance between LOV and MOV. Okay, I guess we should code this thing up, but have a better look at this. Okay, this thing will take two strings and return the edit distance. And recursively, first we will go recursively, how to write this thing recursively. Okay, we will figure out how to write this thing recursively, and then we will see how we can do some iterative approach. Okay, cool. And tmux kill server, there is no server, so that is much better. Tmux set attach target DSA, I guess. Go to DP, ls, and knapsack. Nope, this is not knapsack, this is edit distance.cpp, and we will have a function that will return a integer. It will be called distance, and it will have a integer. Let's just name them a and b. It will return some answer, and we would have some strings, string s and y, x and y include bits std c plus plus std c plus plus dot h, and using namespace std yo, and here in our main function we would take our first string into x and the second one into y, so that these are initialized, and we will call this function distance function. And here we have three operations. Let's go. Response is to max or does not matter. We can initialize response equals distance of a minus 1 and b. In this case we are removing some character from x and plus 1, the cost for that thing, and then res equals minimum of res and distance of a comma b minus 1, which is equivalent to adding some character to a, and then res equals minimum of res comma distance of a minus 1 and b minus 1 plus x a equals b a b x a equals y b. No matching function somehow. Why is this a Boolean thing now? Okay, okay, no matching call. Somehow we can convert this thing into an integer. I guess that is the problem. Yep, now it is cool. And return rest. But what is going to be our base condition? If what is going to be our base condition? If not b, if not b, then return a plus 1. If not b, then return a plus 1. If our target length is nothing, if it is 0, then we return a plus 1. And okay, so there is some difference between the number of characters there are and between how many, between the index that we are using. So let's say, no, this is fine. A and B represent the number of characters that we are choosing from the starting prefix. Since it is one indexed, we will have to change this to be 0 indexed. And if not B and how many characters there are in A, we would have to pop them. And if not A, we would have to add all of these characters. Return B. That is the cost of that thing. Right. So this is addition, this is removal, and if they are different, it will be called here. That makes sense. Let's see if this works. Cout cost is going to be distance x dot size and y dot size. No, no, not nether. This one is shit. I'm wrong in the wrong folder. Concept dp clang plus plus. This one is called edit distance. Okay, it is running. Okay, yes, I have to provide the string. Love is my starting string. Movie is the target, and the cost is 1, which is not actually correct. which is not correct, right? Yep, it is not correct. Right. If we were to do this again, let's see. And movie cost is wrong. Cost is wrong. So something is wrong with this thing. String X and Y. String X and Y int res equals this thing, and then find the minimum and then return the minimum. Right. Plus one, plus one. Yes. Distance. This is the cost when we are removing one character from from X, and this is the cost when we are adding one character into A, and this is the cost when we are checking the last one, if the last thing is same in both the things. If it, okay, shit. If it is not, if it is not, then we add the cost. Okay. If the strings, if the characters are different, then we take their cost. Otherwise, we don't, and still the answer is, even though I did compile. Slash now, this thing. Okay, cost is always one somehow. Why? Cost is always one somehow. Okay, if not B, if B equals 0, then return A. If A equals 0, return B. Okay, and okay, then we start with result is going to be equal to distance A minus 1 B plus 1, right? That much is correct. And then we are finding the minimum of the current response that we took, and distance of A B minus 1, and adding 1 to that, 1 to that thing. We are adding 1 to this thing also. Right. That should be correct. That should be correct. Distance of this thing is minimum of this plus 1, this plus 1, and this plus cost. And the cost is if the things pointed by A and B are not equal, then add the cost. Okay. Do I have to change this thing? I think I should change this part. Yep, that much should be cool. I think it will still not work. Let's see. It does work. It shit. Okay, okay. Shit, that seems to be the thing. Shit, that makes sense actually, because this whole thing was being interpreted as a Boolean variable, as a 0 and 1. So even if this thing were to be 2 or something, we would get 1. Okay. And if we start with a string like A, B, C, D, and we want to convert it into a string Z, answer should be 4. It is 4, so that is cool. That is cool. We have written a function that finds the edit distance, so that is cool. That is cool. We can move on to counting tiles. Hello. I can not get used to the sir, but yeah, swappy. And now, counting tiles. What even is this thing? Sometimes the states of a dynamic programming solution are more complex than finding combinations of numbers. Yes, states can be complex. Like, look at this thing. Look at this thing. My first interpretation of this thing is that we have a bunch of squares. We have a bunch of squares, and we want to find the number of ways in which we could put tiles here. And this is very complex. How do we even begin to find a solution to something like this? This looks very, very complex. It is said that this is a 4 by 7 grid, which it is. We have four things here and seven squares on the in the horizontal direction, and the number of solutions is 781. There are 781 different ways in which we can put tiles here. And shit, this is very complex. Shit, this is actually very complex. How do you even begin to solve something like this? This is crazy. Okay, so but we are going to do this, right? Let's see. Sometimes the states of a dynamic programming solution are more complex than fixed combinations of numbers. As an example, consider the problem of calculating the number of distinct ways to fill an n by m grid using 1 by 2 and 2 by 1 size tiles. Shit, that is also important. The number that you see here first is the height, and the number that you see here is the width of the thing. So therefore 1 by 2 is different from 2 by 1. That makes sense. This thing, this tile which is short in height but has a greater width is a 1 by 2 tile, but this tile which seems to be standing is a 2 by 1 tile. So this is also a distinction that we have to make. Okay, for example this, and the total number of solutions is 781. This is crazy. This is crazy. How do you do something like this? This is crazy. The problem can be solved using dynamic programming by going through the grid row by row. So we start with this row. How many possible ways are there if we are just considering this row? And then how many possible ways are there if we are just considering this row? And then also the overlap between the two. Okay, I guess. No shit. You could also, when you are only considering one row, you could consider this thing also as one tile. And this is a Russian character. What is this? How do you create this thing on the keyboard? This is crazy. The problem can be solved using dynamic programming by going through the grid row by row. Okay. Each row in a solution can be represented as a string that contains m characters from the set this, because m is the size of the row. Yes. So a string would contain stuff like this, but you would not have a character like this on the left hand and not a character like this on the right hand, because that would be illegal. But you could also not have this thing at the top row and not this thing on the bottom row. For example, the above solution consists of four rows that correspond to the following string. Okay, this solution can be represented using strings like this. Okay, let count kx denote the number of ways to construct a solution for rows 1 to k. To construct a solution for rows 1 to k of the grid such that the string x corresponds to row k. Okay, okay, shit. If x denotes the string that we have in the kth row, then count kx will give us the number of possible solutions till the kth row starting from the top row with the x string on the bottom row. Okay, okay, we have x as a variable and k is also a variable. We can iterate k from top to bottom and generate new permutations for x and combinations. It is possible to use dynamic programming here because the state of a row is constrained only by the state of the previous row. That makes sense. if we have, even though x is a variable, we have fixed x on some row, and that is cool. And that only gives certain amount of limited possibilities to be had at the row above it, and then at the row above it, and so on. Okay, but this is actually fucking complicated. Look at this. Look at this. What is this? Look at this. We have multiplication 4 into cos square alpha a divided by n plus a cos square pi b. This is not alpha a. What even is alpha a? This is pi a into pi b divided by m plus 1, and we are multiplying this whole thing with our a varying from 1 to n minus 1, upper limit of n divided by 2, and upper limit of m divided by 2, and the time complexity is a bit high, on the higher end. Okay, and yep, so this is complex. I don't think we can even write the code to find this thing just yet. Not just yet, right? Not yet, but someday. Yep, in the next 3 to 4 months we will be able to solve a problem like this. This is complex. Wait, is there a problem like this in the CSES problem set? Some tiling problem? There is, counting tiles, and only 6,500 people have been able to solve this. Shit, this is the input. If you have a 4-7 grid, the answer is 781. This is the exact same question. 4 by 7 grid, 781 is the answer. That is crazy. I think these people talk to each other, and they do. The people who created this problem set are the same people who wrote this book. Courses? Shit, they have courses? That is crazy. But the courses are in Finnish. Like, look at this. Look at this. This is Finnish. This is not English. Now, counting tiles. A solution is valid if row 1 does not contain the character this. That makes sense because you cannot extend a tile upward when you are at the top row. Row n does not contain the tile character this, which makes sense. And all consecutive rows are compatible. Makes sense for obvious reasons. For example, the rows this and this are compatible. Rows this and this are compatible. In what sense? How do you pair this character there? You need to have, shit, there are 5 openings here, and here there are only 3 openings. How do you pair them up? Are compatible, while the rows this and this are not compatible. Okay, I guess it is not very obvious why these are not compatible, why these things are compatible, and these are not compatible. This actually does not make any sense. Why are these two rows considered compatible? How do you, like, you cannot put this thing above this thing and hope that it works, and vice versa, you cannot put this thing. Okay, okay, this makes sense. This makes sense. Okay, 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 okay. It is, these are compatible. These are compatible. These are compatible. Makes, should they were using exotic characters to represent these things. Okay, we can make our own copy. Above, okay, we have something like this. Above, this, above, down, and up. This is our this row, and then we have this thing, which is down like like this, this, and this, and these two are totally compatible because this thing might have something above, right? This is cool. No rule is being broken here. Same thing here, and here we have a tile. Here also we have a tile, and this could have something above it. This could have something below it. And yeah, this is cool. No rule is being broken here, so these two are compatible. That makes sense. I thought to be compatible, they have to be exactly the same, exact matching, but no, these two are compatible. And now, since a row consists of m characters, that is the length of a row, and there are 4 choices for each character, the number of distinct rows is at most 4 power m. The number of distinct rows, yes, and we have n rows, so n into 4 power m. Thus, the time complexity on the solution is n into 4 power m. Why do we have 2m? Because we can go through this many possible states for each row, and for each state there are this many possibilities, so we multiply the two things together and we do this n times possible states for, okay, so we need 4 power m, 4 power, we need, since there are 4 power m possibilities for a single row, and we have to check if it is compatible with the next one, which also has 4 power m possibilities. So in total, 4 power m into 4 power m, which is 4 power 2m, and this fixes one row, and we have to do this for n rows. This does not fix exactly one row because we are going through one row, but essentially we have to do this for every row, because if I have one row here, one here, one here, one here, let's say 4 rows, then I have to do this 4 power 2m process, this thing between these two rows, make this compatible with this, and then make this compatible with this. So 1 for this, 1, 2, and 3 between this and this row. And yes, so that is cool. And this is to be technically correct n minus 1 times, but that is very, we can just take it as n big O of n complexity and asymptotic notation, and 2m, n into 4 power 2m, that is the total time complexity. Makes sense because the factor 4 power m dominates the time complexity. Okay. The previous row, in practice it is a good idea to rotate the grid so that the shorter side has length m, so that because this thing is very high, we would rather have a larger n than a larger m, because m is a exponent, and a single value increase in m has much more effect than n plus 1. It is possible to make the solution more efficient by using a more compact representation for the rows. It turns out that it is sufficient to know which column of the previous row contained the upper square of a vertical tile. Thus, we can represent a row using only characters this and this, where this is a combination of the characters this. Okay, we can combine them. Okay, using this representation, there are only 2 power m distinct rows. The time complexity is this, which is still very high, very high. This is NP hard problem. As a final note, there is also a surprising direct formula for calculating the number of tiles. Shit, okay, maybe not NP hard. We have a direct formula for this. No, shit, this formula has multiplication. We have to iterate 1 from 1 to n by 2 ceiling, and b from 1 to m by 2 ceiling. Okay, that is what we have to do to calculate this formula, but we are not going to do this. This is way too high, way too above our budget at this point. So we wrote something for this edit distance, and now we have to better our dynamic programming by reading some more stuff, or maybe even do some questions on CSCS and read some stuff on dynamic programming here on Introduction to Dynamic Programming, CP algorithms. Hello. Is this pre? Nope, this is not pre-recorded. This is live. This seems to be live. And yep, I guess I can do a few questions on dynamic programming. Dice combination. 75,000 people have done this, so should not be very hard. Dynamic programming, and this is another thing. I have TMUX on CSES. There are a lot of updates in NewVim. Not NewVim in the plugins. NewVim is old, came out in 2015. Okay, now task is to count the number of ways to construct some n by throwing a dice one or more times. Each throw produces an outcome between 1 and 6. Okay, that is cool. That is very similar to the coin problem. In this case, we have choices ranging from 1 to 6. So this should be very easy. Like, I want to get this right in one try. Boilerplate, how are we going to get the input? In input, we would just get a single number that is going to be the target sum. We can remove everything else. And what is the maximum value for n? Answer can be very big, so we have to return the modulo. That is fine. N can fit inside an integer. And long answer equals initial equals, or we don't even need this. The number of ways I would have to create a vector of long of size, I will call it response n plus 1, and I would have a const int m, that is the number with which I want to find the modulo with 19E7. I think making this a long would be better, even though it fits inside an integer. This is still fine. And now we would have a iterative solution. There is res 0 is 1. There is only one way to get a solution. There is only one way to get a solution. No, there are 0 ways, because the thing is, I am not going to throw the dice. So 0 and res 1 equals 1. There is only one way to get a sum of 1. Now I can iterate for int I equals 2, I less than equal to n, and I plus plus. And yep, for this thing, you know, const, no, con choices, which is a matrix 1, 2, and not a matrix, a static array. These are the only choices I could have, right? For this, for int x, n choices if choices if I minus x greater than 0, if I minus x greater than 0, greater than equal to is also fine, greater than equal to 0, then put take the total number of ways. Okay, total number of ways. Okay, and 1 and 2 are distinct from 2 and 1. Okay, go back. If it is this, then add res I plus equals the number of ways to get to that thing. Yep. Res I minus x. And and also take the modulus. Take the modulus on the next line. Res modulus with m. No y will overload. Okay, it is long and long. Why is constant a problem? Because I'm stupid. Shit. Yes, of course. Shit. Res I. Yep, yep. And at the end, I can just see out res bracket n with a new line. Let's see if that works. That is wrong. That is totally wrong. Shit. We start iterating from 2. And okay, that is correct. For 1, 1 and I equals 2. For I equals 2, we would have been able to choose 1 and the answer would be 2. Answer would be one way. Yep. And then when we chose 2, I guess I have to change this to 1. That is correct. That is correct. 1 yeah, that is cool. That is, I do not want to get this wrong. I want to get this right in the first try. So constant int choices. These are the only choices and my base cases are res 0 and 1. And the total time complexity is 6n. Big O of 6n, which is just n. Big O of n is the total time complexity, and we are also taking modulus. Modulus is slow, but that is fine. Now we can submit this and we will see how that goes. C++ is going to be our language of choice, and document the programming, competitive programming, CSES, DP, dice combinations. Let's go. Submit. Pending. Okay. And cool. It is accepted. That is cool. Beautiful. Sweet. Minimizing coins. Okay. Consider a money system consisting of n coins. Each coin has a positive integer value. Your task is to produce a sum of money x using available coins in such a way that the number of coins is minimal. For example, if the coins are this and the desired sum is 11, I can choose 5, 5, 1. Yes, 5, 5, 1, which requires 3 coins. Okay, so the minimum number of coins, this should be pretty easy. Yep, this is easy. This is a standard question in dynamic programming. And yep, and wait, okay, how's the input? The first line has two integers, n and x, the number of coins, and the desired sum. The second line has n distinct coins. that is cool. N and X. Say this, and Vi is going to contain the N coins. Vi is nothing, but vector int is something, and the constraints are not very high. Shit, I can have a coin of 10 power 6, which is messed up. Right, and then for int I equals 0, I less than n, I plus plus, we will get into coins I, the current thing, and now we will create a function, a vector of integers which will contain the answer response of size n plus 1, and we will put rest 0 is already equal to 0, and now we will start iterating for int I equals 0, I less than equal to n I plus plus, and right, for int c n coins, for int c n coins, if I the current, right, we can start iterating from 1, and we don't actually have to do this thing because it is already 0. Int minus c, if this thing is greater than or equal to 0, we will see, yep, the response, we need the minimum value. So res I equals int max initially, that is initialization of this value, and this thing would be res I equals minimum of res I, the current value, and the value, the number of points for res I minus x plus 1 for this current point that we have chosen, that is c, but x is minus x is not a thing. Shit. Minus c, minus c, minus c. Okay, this x does not look good to me. I would like to call it a t, as in target, right? And do I have to change anything else anywhere? Yep, I would like to change this to x. Yep, that is cool. That is cool. And at the end, we should have the answer on res, and res n. That should be our answer. Yep. Is everything cool? Yep, looks like it. Yeah, that is the correct solution. We can go on and submit this, and we have to choose files, minimizing coins, C++20. Yep, that is the one which we go. Hello, bro. Where did you reach in rating on Code Force? On which are you on the rating section on the TLE? Did you attempt chicken jockey problem in yesterday? I didn't attempt chicken jockey, but I got the solution. I was able to come up with the solution for the third one, this one. And yeah, chicken jockey was cool. Chicken jockey was, the problem was cool. I will like to look at the solution for this, but I was able to make a algorithm which works for this problem, but it gave wrong answer on test case 2, on pre-test 2, and yeah, that was bad, and my rating is very low, very low. I lost a lot of rating in the second last contest, and on TLE my rank is fine. This thing, yep, I have to do a lot of practice. A lot of practice is needed. See, a lot of practice is needed. A lot of practice is needed. Look at this. Look at this. Okay, what went wrong? What is wrong? And I will not look at the test cases. As a good dynamic programmer, as a good competitive programmer, choose the minimum of this plus 1. For 0, answer is 0. Right, right. It goes till n. Right. Yep. And why is it giving the wrong answer? That does not make sense. Okay. Did I read the input correctly? Yep. This is the number of coins. This is my target. And this should be the output. Okay. If I have CDDP, if I have minimizing point, let's say I have 3 coins and my target is 4 and the coins are 1, 5 and 7. Answer is 3, which is wrong. Which is 3 is wrong. Answer should be 4. 3 is wrong. Okay, what is this res? See out res. If I have 3 coins, my target is 4 and the coins are 1, 5, 7. This is 0 to okay, it is. Now shit. Okay. Shit. Yes. My bad. My bad. This is my stupidity. Yep. Shit. Yes. Shit. Okay. Now everything is correct. Now I less than equal to t. Yep. Number of coins n. Response t plus 1. Size t plus 1. Right. Go through the whole thing till equal to t. I equals to t and yep. Fill the whole resolution response vector and then output the response value for this thing. Now, if I were to direct submit this thing, it would work. Hopefully. Hope C++20. That is cool. Which rating section on the TLE? Rating section for 1400. Yeah, I was attempting 1400 questions on TLE. Okay, wrong. Shit, this is actually bad. Okay. Int max is my initialized answer. Then x, I'm iterating through all the coins. And if by subtracting this thing from the ith value, if I subtract x coin, the current coin, and if the target value remains 0 or greater than 0, then update the resolution, the response value, which resolution response value I equals minimum of whatever it was and this thing response value for I minus x plus 1 for the x coin that we are using right now to get to this ith sum. Okay, this does not make sense actually. This shouldn't be giving any trouble. 1, 5, 7. Answer is 4. That is correct for this thing. And we will not look at the test case or the test case in which we got the wrong answer. Not yet. If we can figure out the answer on our own, that would be very cool. And this is not even that difficult. Is it because of the constraint? Okay, shit. If it is not possible to produce, is that also the case? If it is not possible to produce the answer. Okay, shit. Okay, shit. Okay, shit. If res t smaller than int, shit, I should have read the problem statement. If it is smaller then the thing, then this, else C out -1 with any line. Yep. If I have, let's run this again. I have just one coin and I want to reach the sum of 1 and my coin is 2 -1. Beautiful. Shit, I should have read the thing properly. That is always a good thing. Minimizing coins, submit. Yep. If there is number 1 in the array, then it might not be possible to get the target. Yep. If there is no 1. Int max is the default value. Yep. Int max is the default value. Yep. Shit. Brr. Okay. Could this be overflowing? Yes, yes, shit. This could actually be overflowing, maybe. I think. Yep. Let's see. But make this infinity and or maybe the default value. Yeah, default value has to be very big. I can make the default. No. The default value can be equal to the target sum actually. The default value can be equal to the target sum. Yeah. And if this thing is lower than t, the default value can be equal to the target sum. That is cool. That is cool. This will not even overflow. Yep. Yep. That seems correct. 1, 1, 2, -1. Cool. And for something else, not slash out, if I have, let's say, 3 coins and my target is 7 and the coins that I have is 6, 2, 5. Answer is 2 somehow. Yes, it is if I use 2 and 5. Shit. I have 3 coins like this, 6, 3 and 5. Answer is -1. That is cool. So I think I didn't have to re-choose the file, but anyways, no file chosen, and now I have to. Shit. Hmm, hmm. How am I getting wrong answer on the first one? Okay, that. Shit, okay, shit. Okay, so I need a better default value than this. N plus 1 would be, t plus 1 would be fine. T plus 1 would be fine. Yeah, shit. T plus 1 would be fine. Shit. That's it. T plus 1 is the default answer value. If this thing is lower than t plus 1. Yeah, t could actually be the answer. T plus 1 is never going to be the answer. Shit. Okay, cool. It shouldn't have taken me 4 attempts to get this one right. This is very basic DP question. 4 attempts is way overkill. Okay, now moving on to the next question. And what was the thing in this? The thing in this was just normal, minimizing the number of coins. This is a classic dynamic programming question. Now, coin combinations. Consider a money system consisting of n coins. Each coin has a positive integer value. Your task is to calculate the number of distinct ways, that is the thing, distinct ways you can produce a money sum x using the available coins. Money sum x using the available coins. Distinct ways, for example, if this and the desired sum is 9, there are 8 distinct ways. These two are not distinct. Okay, order does matter in that sense. 2 plus 2 plus 5 is different from 2 plus 5 plus 2. Okay. And isn't this the same as the first cube problem, dice problem? Okay, how is the input? Print one number modulo this thing, very big prime number. The second line has n distinct, and the first line has n and x. N is the number of coins, x is my target sum. Okay, ans is what I need. Boilerplate, CSE, int n and t, cnn, cnn, t, and vector, integer, coins, size, t plus size n, shit, for auto, reference, x, n, points, c in x, and then response, vector and response, t plus 1, and cons int m equals 1 e 9 plus 7, right? And then for loop int I equals 0, I less than t less than equal to t and I plus plus. And where do we start? A response, the number of ways to get a sum of 0 is 0, for 1 depends, right? And if there are no ways, then there are no ways. What is going to be the default value? Okay, yes. If there are no ways, then 0. Default value is 0. Total number of ways. Yep, default is 0. So that is good. Now, for in x and points, and if I minus x greater than equal to 0, then rest for I equals rest for I minus x, not equal, plus equals. We are using the x point, then the number of ways we can get to x minus coins, I minus x coins, add that to this and iterate for all the coins, and at the end, not at the end, before this, we have to take modulo res I modulo with m, because this could be very, very big. We do not want that. Res for target, a new line. And I want to get this correct in first try. That would be cool. Okay, I am taking in n, then I'm taking in n, then I'm taking in the number of coins. N is the number of coins, t is my target. Then I create a response vector of size t plus 1. That is correct because response is 0 indexed. Then my modulo, and I iterates from 0, it can iterate from 1. 1 is fine. 1 is fine. Then I iterate through all the coins, and if I use the x coin which I am at, if I use it and the target is greater than or equal to 0, if it is non-negative, then I add to my res I the number of ways for that I minus x coins, take modulus, and then at the end return this. So I am going to directly submit this without even locally checking, and I want to get this right. Coin combinations, Coin combinations. C++ 20 is the thing. It's yeah, and maybe I should have checked locally. Maybe I should have checked locally. Shit, 8. Okay, am I not even getting 8? I'm getting 0. I'm getting 0, which is crazy. Wait, shit, number of ways. My base condition is messed up. Rest 0 is 1. There's only one way to get a sum of 0, which is 1. Shit. Shit, this is bad. This is bad. Now it will be correct. Now it will work. Now it will work. Shit. Shit. My base condition was messed up. Shit. Should have been right in first try. Coin combination. C++20. And now testing. Accepted. Shit. It was just this base condition. The singular base condition. Shit. And shit. This is even bad. Like even worse. Because I just did the same base condition here. Shit. I can actually remove this and start iterating from 1. Like, shit. Anyways, moving on to the next question. Coin combinations 2. And now is the thing. Now is more difficult. Yeah. Because here we have only 3 ways for the same sum. Why? Because now we are considering 2 plus 2 plus 5 different from 2 plus 5 plus 2. So no permutations. Ordered way, distinct ordered way. You can produce a money sum x. Yep. And this is the problem of double counting. I saw this in Eric To's dynamic programming video, and this is cool. And n target, c in n and t, and then vector for storing coins size n for auto x and a. What is a? A is nothing. Coins c in x, and then a response, a vector, integer, a response size t plus 1 is going to be the size, and then we are going to iterate. But this is not enough. This is not enough. This is not enough. We need to have a 2-dimensional vector, aka a matrix vector int, and the size is going to be the size of the coins vector int size of the coins, which is n. Size of the coins as in the sense the number of coins that we have, and then for int I initially fill. Yes. Shit. Okay. Coins plus 1. Coins plus n plus 1. N plus 1. Because the state that we are going to store is a bit more than what we usually store. This will show us if to get to a sum of t plus 1, to get to a sum of t, also sort coins dot begin and coins dot end. Right, now it is sorted. So since to get to a sum of 9, I could choose 2 plus 2 plus 5, which is correct. 2 plus 2 4 plus 5 9. or I could choose 2 plus 5 plus 2. That is also the same thing. Or I could choose 5 plus 2 plus 2 get to a sum of 9. But these are the three permutations for the single thing. I do not want to overcount the same thing again and again. So what we are going to do is, among these permutations, we are not going to count these two. And what is the factor on the basis of which we are eliminating these two? The factor is that this one is lexicographically the smallest. And what does that mean? If we were to arrange these numbers like this, removing the plus in the middle, 2, 5, 2, and 5, 2, 2. So among these three numbers, this one is the smallest. And given all the permutations, we are going to take the smallest permutation. So in our list, in our vector, let's say the target is 9. Target is 9 actually in this example case. And we have the points 2, 3, and 5. 2, 3, and 5. 2, 3, and 5 are our points. We would have a vector going from 0, 1, 2. Let's call this 4. Right? Let's say our target is 4. So we would have a vector going from 0, 1, 2, 3, 4. And coins, no coin, the second coin, the coin with the value 2, the coin with the value 4, 3, and the coin with the value 5. So what we have here is, what are the number of ways to get to a sum of 0 when I'm using 0 coins? There is one way. What is the number of ways to get to a sum of 0 when I'm using the coin with the value 0? No ways. Same here, no. Same here, no. What is the number of ways to get to a sum of 1 when I'm using 0 coins? No ways. What is the number of ways to get to a sum of 1 when I'm using 2 coins? No, and no here, 0 here. And then this thing. What is the number of ways to get to a sum of 2 when I am using 0 coins? 0 ways. There are no ways. For 2, there is one way, because I can use the tooth coin here and get to a sum of 0. And yeah, this when 2 is my last coin. And here, 0 here, 0 here, and then when I want to get to a sum of 3, how many ways can I choose when I'm not using any coins? So 0. How many ways can I choose when I'm using the second coin as my last coin? Second coin as my last. So before this, I would have one coin to get to a target of 1. And how many ways can I use? And since I'm only considering lexicographically smallest ways, so in the 1, when 1 is my target now, I can only either have here 0, 2, or no coins at all. And in that range, I cannot reach the sum of 1. So answer is going to be the same. Answer is going to be 0. And then to get to a sum of 3 is 1, to get to a sum of 5. To get to, no, when I'm using 5 as my last coin, I cannot get to 3. When I'm using 4 as my last coin, I cannot get here. With 0 as my last coin, with 2 as my last coin, there is one way. With 3 as my last coin, 0 ways, and with 5, 0 ways. So this is going to be my answer, the summation of this whole thing. And I think I haven't done a very good job at explaining this thing. But yeah, that is how we do things. So after sorting, for int I equals 0, and I would also have to put some base condition, some really good base condition, I plus plus. And is the screen visible? Yep, it is, and I'm not in the center. Okay, now, cool. What do we have? Now we will start it. Yep, what do we know at the start? At the start, to get to a sum of 0 using 0 coins, there is one way. That is what we have to do, and fill everything else with 0. Everything else is already a 0. So res 0 using 0 coins is 1. That is just how things are. And now we can start iterating from I equals 1 to get to a sum of 1. And yep, for for int I, and for every value in this grid, I have to go through every value before it. If I'm here, then I have to go through every value before it. Not exactly in this row, but in this case, to get to a sum of 4 using 5 as my last one, there is no way. Yeah. When 3 is my last one, then I need a sum of 1 using 0, 2, or 3. There is no way. For int x equals 0, x less than equal to the number of coins, which is n, and x plus plus. So x represents this coin which I am at currently to get to a sum of this, and that is going to be the sum of, I would have to see a few things. If I minus the xth coin, which is coins x, if it is greater than or equal to 0, only then could I achieve it. And if I can, then I need to iterate from 0 till x using some shit. This is for loop inside a for loop inside a if statement, which is inside a for loop, which is inside another global level for loop, which is inside the main function. That is very bad. J less than equal to x, I can go up to x and j plus plus. And the default response is going to be 0, which it already is 0. And to get to a sum of I using x as my last coin plus equals response to get to a sum of I minus coins x, yes, and the last coin that I'm using is j. That should be cool. This should be actually cool. That should be cool. And modulo, I have to use modulo. Yep, answer can be very big, modulo. And let's call it 1e9 plus 7. After taking these sums, I would have to do modulo equals m. Take its modulo with m, and the only thing that remains seems to be the int answer initially equal to 0, but I could use the accumulate built-in library function, but that is not going to give me the modulo. That is not going to give. I can actually make this a long and now use the accumulate function. Accumulate on res t dot begin and res t dot end. Accumulate starting with 0. Okay, I thought I would get an error if I don't use L00, but I guess that is already automatically converted. And then cout answer modulo m. Okay, seems to be right. Seems to be right. I also have the base condition ready. Let's see if it works here. And that is the wrong answer. 9 is the wrong way to go about things. Shit. 9 is actually the wrong way. 9 is the wrong thing. Shit. Yep. 9 is wrong. 9 is totally wrong. So I messed up at some place. I minus coins X J, where J, and it is sorted. This thing is sorted. Zero shit. Whenever I make a row, let's say I output the row, that's I output, and there is no overload. So we make our own overload. Lang plus plus. What is even the name of the question? Coin combination. I, which is like second. O is nothing. Dot slash out. We have 3 coins, and the target sum is 9, and the coins are 2, 3, 5, and that is the answer. Okay, so this thing is way overblown. Even this thing. Okay, this should not be 2. Why are there 2 ways here? This whole row should have been this whole row should have been 0. How can I get to a sum of 1? Okay, this does not make sense actually. I take in the coins, then I sort the coins, the out coins. 3, 9, 2, 3, 5. Those are the coins. It is because I'm very stupid. Shit. Makes sense. Brr. Okay. X will start iterating from this, but it will not go till n, which is bad. Do not go till n. And yes, if that thing is greater than or equal to 0, start iterating from this till less than equal to x. Or I could translate x. Yep, I could translate x. Go till equal, and this would actually mean when I'm going to coins, x minus 1. Go till x, and here x minus 1. I think we are good. We should be very good here. Blank. Using 9 coins to get to a sum of 9, 3 coins. Yep, that is correct. That is correct. But is it going to work there? Again, at least remove the extra code. Debugging stuff. Yeah, I think that is cool. Let's see. Yep, that seems correct. Is it? Wait, I want to check. Is n is the number of coins, t is my target. Then I take in the coins right here. I'm taking in the coins. Then I sort the coins from smallest to biggest, which is also correct. And then response is a two-dimensional vector, a matrix, aka, and then yep, the modulo with which I'm going to take modulo, yep, and initialize 0, 0 equals 1, which is also correct. That means to get to a sum of 0 using 0 coins, there is one way. And then I start iterating for sum equal to 1 and the number of ways. If I can never get to a sum, then answer is going to be 0. Okay, it seems correct. Wait, is it x is 1, that is using 1 coins from the start till using all of the n coins, the nth coin, not all of the n coins. And if using this coin is greater than equal to 0, then start iterating for the coin whose value could be reached, which is I minus coins x minus 1, and j is always either equal to this xth coin or lower than this, and take its modulus. Okay, I'm confused a bit about this bit. This seems to be correct. J represents the number of coins, 0 indexed, 0 coin, all that, and x represent from 1. 1 means 1 coin. Yeah, so yeah, they are on the same domain. Yep. Minimizing coins 2. CCT 20 testing and wrong. TLE. Okay, TLE is fine. TLE is fine. I have to remove this loop, this inner loop. This is bad. Right now the time complexity is T, which is can be very big. This thing, now we have to optimize our solution. N is 100, X is 100, 10 power 6 target, and the value of a coin could be 10 power 6. Okay, here is one loop till T 10 power 6 at in worst case, and then a loop till N. Okay, there is a N square loop, and N at max is 100. So 100 into 110 power 4 into the outer loop of 10 power 6, that is 10 power 10, which is bad. So we have to somehow eliminate this loop. I think using prefix. Yep, using prefix. Yep, using prefix. Fill res 0 comma begin and res 0 comma end with 1 with 1. So in this representation, which looks very bad, green color is not good. Green is like low-key is good, but yeah, green does not look good here. 0, 2, 3, 5, 0, 1, 2, 3, 4, and this was 1. Now our prefix is going to be like this, and this was 0, so it is going to be 0, and this was 1 here, this was 0 here, and then 1, and it is going to be 1 again on every place, everywhere. Now 3, it was 0 here, and should be 0 here, should be 1 here, and prefix 0, using 2 as the last point, 1. Now using 3, 0, but this is a prefix, and 1. Yep. And at the end, my answer would be this thing, this value. Yeah, that is cool. That is cool. So everything here is now filled up to 1. everything here is 1, in the rest 0, begin till end, everything is 1. I think that is what the fill function does. Okay, there is just syntax. Inline constant expression void fill wrap iterator integer pointer. Shit. Okay, and then we are iterating starting from this value till this thing, and internally we will iterate through this. And what we are avoiding is when I am at a step like this, then I am avoiding iterating through these things. I can just look at this value, and whatever the value here is, it would be the sum of this value and this value, and this is what I have here. 1 plus 0 is 1, 1. Yeah. Now, there are a few questions that I have to ask myself. Yep, if it is possible to go back there, what is the default value here? The default is 0. X starts at 1. Beautiful. X starts at 1. X starts at 1, and every value here is 0. So I can always look back because I am starting at this index. I can always look back. I'm not starting here, so I do not have to think or worry about segmentation fault. If this, then res I using x as the last coin equals res I using x minus the value for the last coin plus res I minus coins x minus 1 x. Yo, 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 yep, using x as the last coin. And the answer is going to be, and also modulus res I x mod equals m. What do we have here? Res target when I'm using all of the coins. Yeah, since it is accumulated sum. N. Yep, that is my proposition. Seems to be wrong. I say 2, but I want to say 3. 2 is not how we go. Albert Camus. Shit, this is wrong. Uh, yeah, cool. Fill response C out T when I want to get to T, and I'm taking the last bit, which is this, which is this, which is this. And if I extend this table 5, 6, 7, 8 till 9, if I extend this till 9, here everything is 0. I can say everything is 0. 5 using 2 as last bit would be one way. No, yep, 0 using 2 as the last bit is 0, which is this plus this. Yep, and using 3 as the last bit, answer is 1. And using 5 as the last bit, answer should be 2. Yes, and then for 6 using 2 as the last bit, answer is 1. There is one way. Using 3 as the last bit, answer is 1 plus 1, 2. 2, this one plus this one, 2. And using 5 as last bit, answer is 2. Cool. Then for 7, using 2 as the last bit. No. Using 3 as the last bit. Here is 1. So yeah, 1. And using 5 as the last bit. 2. Using 2 as the last bit. Here, 1. Using 3 as the last bit. Here, 1 plus 1, 2. Using 5 as the last bit. Here, 1 plus 1 plus 2, 3. Yep, cool. And for 9, using 2 as the last bit, there is no way. Using 3 as the last coin, I would have to go up to 6, which is 2 actually. And using 5 as the last bit, 4, 3 is what I output. No, 3 is the correct answer, but I say 2 somehow. Why do I say 2? Okay, some debugging things, debugging code. Using 3 coins to get to 9, and the 3 coins are 2, 3, 5. Okay, that is wrong. That is wrong. That is wrong. It does not. Okay, fill. No, that is 1. That is 1. For 2, we have 0. 1, 1, 1. Okay, this is not prefix. This is not actually prefix. Somehow something messed up. The last one. Yes. Huh. Okay. This does not behave correctly. Initially, every value is 0. And this is prefix. This is I response for I x minus 1 plus I x going back to the coin using the x coin. This is somehow not prefix. Why? Res I x res I x minus 1. Yep, should have worked. Fine. When I have a value here, yep. Yes, when I have 1 here, I should always have at least 1 here. Even if not, I'm not, even if it is not increasing, I should at least have 1 there. So therefore, this thing does not make sense. Response I x equals response I x minus 1 plus the response for using the xth coin for getting a sum of response I minus x coins x minus 1, I minus coins x minus 1. Why is this not prefix? Okay, okay, because of this, because of this. Okay, okay. Yep, yep. Now here I have to check something. I minus coins x minus 1. If this thing is greater than equal to 0, question mark, then this else 0. And now everything should be beautiful, as in like art. That seems cool. That seems cool. Shit, we haven't read the analysis for any of the questions that we have submitted till now. We have done 3 questions. We are on the 4th one, just on the verge of doing 4th one. And we haven't read the analysis for even a single one. AC plus 20, let's see. Coin change 2. Still time limit exceeded. Still. 10 power 6 into n 100, which is 100. Is this operation too big? Or this thing is a modulus too big? Is the modulus too big? It could be, maybe the modulus, because modulus is very slow, right? Yep. Is there a faster version? Mm, Custom faster version, faster than the standard library version? Shit. The time complexity is not bad. I need to reduce the constant. I need to reduce the constant factors. Well, taking in input is fine. Creating this vector is fine. Taking in the coins is fine. Sorting the coins is also fine, which is at max 100 coins. Is it already in sorted order? The value of each coin. Yeah, they are not guaranteed to be in sorted order. Then creating a vector. Vector is also fine. 10 power 8 would be the worst thing. If I am storing integers of size 10 power 8, 10 power 8 integers, 10 power 8 integers, one integer takes 4 bytes, and 4 bytes into 10 power 8, that would be 1 kilobytes is 4000. I have taken 3 zeros from this. I have 5 remaining, and then 1 MB would be, or 4 MBs would be taking one more bit off. Then this is GB. Yep, if I take 3 more off, this becomes 4 GB, 4 kilo. This is 4 GB. Shit. 4 GB, and I still have one remaining. So 40 GB of space. 40 GB of space to solve a single problem. That is way too high. So I have to do something about my memory usage. Memory usage. Here having a t plus 1 row is fine. T plus 1 is it necessary? Can I write conditional logic and avoid storing this state? Yeah, time limit exceeded somehow. And okay, I guess we can come back to this later. Time limit exceeded is the only error. Time limit exceeded is the only error I am thinking about. Modulus has a constant factor, very high constant factor, and then yes, fill is fine. Fill is very fine. This is fine. I'm using a lot of memory. So the error is between in this line and in this line. I have to optimize these two somehow, which we can look into at some point. For now, introduction to dynamic programming, and there is one more thing we could do, support them, add free volunteer run. That is cool. Shit, there is even a Discord. What is this? The whole file. Shit, that is crazy. Feed RSS created.xml. This XML file does not appear to have any style information associated with it. The documentary is shown below. This is shown to be shown to me by my browser, Brave. Okay, introduction to dynamic programming. That is what we are going to read about now. A little bit more water. Cool. Introduction to dynamic programming. The essence of dynamic programming is to avoid repeated calculation. Often dynamic programming problems are naturally solvable by recursion. And okay, do we understand that much at least? The essence of dynamic programming is to avoid repeated calculations. That makes sense. And often dynamic programming problems are naturally solvable by recursion, because recursion is the problem. Recursion is used in problems where there are sub problems of smaller size but the same problem. So it fits well with recursion in that sense. In such cases, it's easiest to write the recursive solution, then save repeated states in lookup table. Table is the thing. Table. Dynamic programming is very related to table, is what I have heard. Then save repeated states in a lookup table. This process is known as top-down dynamic programming with memoization. Top-down dynamic programming with memoization. That is, we have the big problem, and we are recursively breaking it up into smaller problems, and we are creating a table, which is the memoization part. That is read memoization, like we are writing a memo pad, not memorization. Memo pad. Okay. Memo pad. Memo pad is apparently something. Memo. Okay. One of the most basic classic examples of this process is the Fibonacci sequence. Its recursive formula is this. Recursive formulation, not formula, is this. Fn equals, yeah, Fibonacci number of n equals Fibonacci number of n minus 1 plus Fibonacci number of n minus 2, where n is greater than or equal to 2. Otherwise, f of 0, fib of 0 is 0 and fib of 1 is 1. In C++, this would be expressed as this, but this is very bad because the time complexity is 2 power n. See, 2 power n. The runtime of this recursive function is exponential, approximately 2 power n, since one function call fn makes two other function calls. So if you have n things, they will make 2 power n function calls. Results in two simultaneous sized function calls. We can actually test this hypothesis. N fib of CPP. We can write two Fibonacci numbers. Fib recursive takes in a number n and if n equals 0, it is if not n, return 1, and if n equals 1, return 1, right? And else return f of n minus 1 plus f is nothing, fib recursive n minus 1 plus fib recursive n minus 2. That is our recursive formula, which is very bad. Int n taken n from outside, also import stuff, include bits slash std c++.h using namespace std, and in here after taking this we will out fib of n is fib of n, a colon would be very nice, fib recursive n. Lang is nothing, clang is something, or clang plus plus is even better. Fib, find the Fibonacci, fifth Fibonacci number, 8, turns out to be 8. Go a little space there. Let's find the 10th Fibonacci number, 89, cool. 100, 100 might be actually too big. 20, 20 is fine. 30, 30 is also fine. 40, 40 took a little bit of time. 50, 50 is going to take its sweet time. And during that time, we can write fib takes in a number. This is going to be iterative, and we are going to run a loop for int I equals 1 till I less than n and I plus plus. We have two things. Either we could store the state, or we could not. I think let's begin with storing the state. Vector int fibo size n plus 1 and fibo of 0 equals fibo of 1, which is equal to 1. And we are starting to iterate through 1 and equals, and fibo of I equals fibo of I minus 1 plus fibo of I minus 2, and at the end fibo, yep, at the end return fibo of n, which is very cool. And instead of our earlier recursive stupid function, we are going to call this new, better, more beautiful function. Okay, it gave wrong answer because or we could just say define int as long, except this one has to be int 32 t. Yep, clang fib, and now we are using our latest function. Let's call 50. Shit, that is bad. That is very bad, because we are still using the stupidest recursive function. See, there is still no answer, but now compile, run for 50, instantaneous. For 100, instantaneous answer. And 400 it is, and 400 if you were going to take, like, use the recursive function, it will take you ages, years. We can actually, let's try to calculate how much time it will actually take. Since we know the time complexity is 2 power n, and now we want to find out how much time it would take for 2 power 100 calculations. And we are going to assume that 10 power 8 takes 1 second on a normal computer. That is the core forces assumption. How much bits are required? 2 power 31. 2 power 31 is, yeah, 2 power 31 e is very equivalent. 2 power 31 is 2 into 10 power 9. So 2 power 30 is going to be 10 power 9 equivalent, 10 power 9. And there is, the difference is 1 magnitude. Difference is of 2 into 2 is 4 into 2 into 2, 2 power 3 is 8, and the difference between 10 power 9 divided by 10 power 8 is 10, and the best we can approximate using 2 is 2 power 3, so we can remove 2 powers, 3 things from this, so 2 power 7. We can assume this to be equal to 1 second. This many calculations will take 1 second, and we have 2 power 100 calculations. It is going to take its sweet time. So our answer is 2 power 100 divided by 2 power 27, which is 2 power 73 seconds. Let's see, if we have this many seconds, how many minutes there are, and we can use approximations. We can say 1 minute, we can say instead of 60 seconds, we are going to use very bad approximations. Instead of 60 seconds, we can say 64 seconds in 1 minute. And we can say the same for hours. So 64 minutes in 1 hour. And days, instead of 24, let's say 32. That is a very bad approximation, and this will give us a very smaller answer than what is expected, but given the magnitude, it does not matter, it won't matter. So this is how many seconds there are in a day in our given, like, with our approximations, which are very bad approximations, which where we are taking 32 hours in 1 day. And how many days in a year? 526, of course. 215 and 256, 512, 512, 512 days in 1 year. We are going to take 512 days in 1 year. There are 512 days in 1 year. And okay, so there are this many seconds in one hypothetical year that we have conjured up. And how many powers of 2 does this belong to? This would be uh, how many 6, 6 for this, 6 for this, 5 for this, and how many 9 for this. 6 plus 6 plus 5, 12, 17, 26. 2 power 26 for 2 power 26 seconds in one hypothetical year. And in total we had 2 power 73 seconds. So 2 power 73 divided by 2 power 26. What does that give us? 2 power 50, 47 years. 2 power 47 years. That is very big. That is very big. That is how much time. And this is a lower approximate because we have chosen numbers to be very high, higher than their actual values. So this is a lower approximate. Actual value is going to be bigger than this. And that is how much time it is going to take you if you were going to call the recursive formula for calculating Fibonacci sequence without memoization for just finding the 100th value. That is big. That is big. Universe is what, 4 billion years ago, 13 billion years old, which we can approximate to 10 power 10, and we did approximate 10 power 8 to be, yeah, we did approximate 2 power 27 to be equal to 10 power 8. And right here we have 100, a factor of 100, a factor of 100, or 2 power 30 is very equivalent to 10 power 9, and above this we have to multiply both sides by 10, and we can approximate 10 by 2 power 3, which just adds to, so into 2 power 30, very approximate to 10 power 10, we have 2 power 33, approximately the age of the universe in years. 2 power 33 years. And our solution for this was 2 power 47. So if we divide the 2 power 47 divided by 2 power 33, that is 2 power 14. 2 power 14. Shit, this is a calculable number. That is actually calculable because 2 power 10 is 1024 and 2 power 4 is 16. So just multiply this number by 16. And what is it going to be? 16 for this, and this number multiplied by 16 is going to be 160, 320, 320 into 4, 16 into 4, 64, 384. 2 power 14 should be 16384, 2 power 14, yeah, 16384. So to calculate fib of 100 using a recursive formula, it is going to take 16384 times the age of the universe time. Yeah, that is very big. So we should not do this. We should instead use iteration. Iteration is much better. Yep, speeding up Fibonacci sequence with memoization. And before we begin with that, I would have to go to the washroom and I will be right back. Yep, I'll be right back in a minute. think I should put my phone on charging. Now it is charging, and yep, angle is good. Angle is fine. Things. My mic was way over there. Now better. Yep. And yeah, I always have this. I can always put this up. That is cool. And now speeding up the Fibonacci sequence. What is speeding up the Fibonacci sequence itself? I have to speed up the process of finding the Fibonacci number. Our recursive function currently solves Fibonacci in exponential time. This means that we can only handle small input values before the problem becomes too difficult. For instance, F29 results in over 1 million function calls. This could even result in stack overflow, right? 1 million recursive calls. Shit. Yes. We wrote, okay, let me show you. CD assembly in a stream at some point. We wrote how to find Fibonacci sequence in assembly. And this one is compare with 1. If 1, then go to end. And yep, I think this one uses recursive thing. I have hard coded the number here, fib of 10. I'm trying to calculate here fib of 10. And then I'm calling this factorial function here, linking to this factorial function here. And after finding it, we are printing the thing by calling printf function, branching link to the printf function. And inside our factorial function, we have the value whose factorial we want to find in register 0. And we are storing stuff which we have to do, mandatory stuff when function calling in assembly. Compare the value there with 1 if it is, then exit. Yep, if it is, then exit. The answer should be an 1, register number 1. Wait, this is actually not really correct. No, this is fine. This is fine. This is fine. Otherwise, multiply. Shit, this is not calculating Fibonacci. This is calculating factorial. My bad. Tmux attach T TSI, I guess. Yeah, cool. Now we can continue with our reading. How to speed this up? F of 29 makes 1 million function calls, which is bad. To increase the speed, we recognize that the number of sub-problems is only O power n, big O of n. That is, in order to calculate f of n, we only need to know n minus 1, n minus 2 until 0. Therefore, instead of recalculating these sub-problems, we solve them once and save the result in a lookup table. Lookup table. Tables are very important in dynamic programming. That is the whole thing about dynamic programming, tables. Subsequent calls will use this lookup table and immediately return a result, thus eliminating exponential work. And if you want to read about dynamic programming, you can also go to CLRS. CLRS is just the name of this book, Introduction to Algorithms. It is called CLRS because of the names of the writers. C. Corman, L. Liserson, R. Rivest, Ronald Rivest is a nice man, and S. Clifford Stein, CLRS. There is a bit about, not a bit, a whole chapter on dynamic programming right here. Before Greedy, they teach about dynamic programming, and there is this rod cutting problem, which is cool. I wrote a little function for this. Right here, rod cutting, and this does work. 40. Okay, anyways, Cody, it is looking. This happened because I have hard coded the values. That is why I just got the answer. So that is cool. You can go there and read about it. But right now we have to cover this article. Each recursive call will check against a lookup table to see if the value has been calculated. If it already has been calculated, then we won't calculate and we can return in constant time if we have previously calculated it. Return the value, otherwise we calculate the function normally, making calls. And the number of calls is going to be O of n from that point. We don't have the answer. This is an enormous improvement over our previous exponential time algorithm. And this can even speed up our stupid recursive function. Not edit distance, but fib. Wait, where is our fib question? Wait, did I delete it accidentally? Point fib. I was in CACS. Yes, makes sense. I was not here. I was here. Yep. Where we have fib. This can even speed up our recursive approach. If we have a table, let's say we have a vector of integers, let's call it just table. And after we get our input, we reassign our table dot assign with size n, or to be more exact, n plus 1 would be nice. No matching function call, yes, because we have to give a default value which is 0. And yeah, table 0 equals 1. Just that much should be fine. And if not, here, if table n, then return table n. Otherwise, do this, and the base case is already handled in the table. Yep. We don't even have to do this here. We can do this here. And before just returning, table n equals fib recursive of n minus 1 plus fib recursive of n minus 2. And then return that. Table of n, return table of n. And here, if not n, then return 1. If it is 0, then return 1. This should speed up our recursive function also. Fibonacci, let's go 100. It does speed up, but the answers don't match. Answers don't match. Why is it negative? Negative does not make sense. Overflow, but no, I am defining integer as long. There should be no overflow. If table n return table n, initially everything is 0, that is cool. If not, if n equals 0, cool. If table n is not 0, then return the value of that thing. Otherwise, if maybe, yeah, if not n, then table n, table 0 equals 1 and return 1, not n. That is blank backslash out and find fib of 50, which is very big than it is supposed to be. Yep, why am I getting this massive number instead of this number, which I should be getting? Fib of 12. Okay, seems to be there are some bad values. Fib of n minus 1, return table n. Are there some garbage values? No, there are no garbage values. After calling this function, print the table. Let's see, for 12. That is wrong. That is very, very wrong. What do I get for 1? That is very, very wrong. Size is n plus 1 and default value should have been 0. When I call this function, no, this is the function. Yes. Recursive, if not n, then this, right? If table n is not equal to 0, there seem to be some garbage values somehow, even though I am doing table.assign before calling my Fibonacci sequence recursive function. Table 0 equals 1, return 1 if table n, that is if I already have the value. Maybe I can use a little minus 1 here, and here if table n not equal to -1, then return that thing, whatever it is. Let's see, maybe now okay, now it is correct. Now it is cool. 1000th value. Yeah, overflow. That is fine. Yeah, this is actually pretty cool. Maximum is 100. Found, you can initialize everything to something, but yeah, you can also use memory instead of that compute power in which you go through all the values and initialize them to -1 or 0. That is also cool. For function, if found, then return that thing. Otherwise, if n equals this or this, then do this. And put found n equals to this. And this is better. This is actually better. Go to the first line, v, f, this, delete, go down, front, v, f, this, paste. This is better. I'm also assigning the value and I am returning the same value. That is cool. This is cool. This thing. Now with our new memoized recursive function f of 29, which used to result in over 1 million calls now results in only 57. 57 is, yeah, okay, 57. Clearly 20,000 times fewer function calls. Ironically, we are now limited by our data type. Yes, this is the last Fibonacci number that can fit into a 32-bit integer. Typically, we try to save states and arrays if possible, since the lookup time is... Shit, my phone is actually not charging. My bad. Yep, now it is. That is cool. And am I visible correctly? Yes. Yep. Here I am. With our new memoized function, recursive function f of 29, which used to result in over 1 million calls, now results in only 57. Nearly 20,000 times fewer function calls. Ironically, we are now limited by our data type. F of 46 is, yep, that can fit into a 32-bit integer. Otherwise, all the numbers bigger than that are going to be really big, and we will have some overflow, which is bad. Typically, we try to save states in arrays if possible, since the lookup time is constant in arrays with minimal overhead. Yes, that is important. Even though the lookup time is constant, often the overhead, the constant factor has to be lower, and it is very low in arrays. Those are cool. However, more generically, that is a term, we can save states any way we like. Other examples include binary search trees. Yeah, that makes sense. Storing states in arrays is just one of the options. You can store them in any way you want, unordered map or map. Yeah. Hash table is unordered map. Unordered map constant time is very high in unordered maps. And binary search trees map, normal map. An example of this might be this: when we are using unordered map, integer, if this thing, yeah, makes sense, fib of 1, 1, fib of 2, 3, function. If we have the nth number, then return n, memo n. Otherwise, do this and return here this, right? Or analogously, an analogy. The same thing with map. This thing uses hash table and has constant, very high constant factors, unordered map. But this thing, even though the time is not constant, it uses log n time, which is much better than very high constant factors here. Both of these will almost always be slower than the array-based version for a generic memoized recursive function. These alternative ways of saving states are primarily useful when saving vectors or strings as part of the state space. That makes sense when you saving vectors or strings. The layman's way of analyzing the runtime of a memoized recursive function is this: work per subproblem into number of subproblems. Yes, work per subproblem is something like not much, right? It is constant. We are not iterating through every subproblem. And how many number of subproblems there are? The number of subproblems are, it still seems to be 2 power n, not 2 power n, because if I already have called n for some value, I'm not going to call it again. So n number of subproblems is n, because if I have already called n minus 1, I'm not going, and I will see it here, and I will not call this function again. That makes sense. Using a binary search tree map in C++ to save states will technically result in n log n, if we are using binary search trees, that is. as each lookup and insertion will take this much time, and with this unique subproblems we have this much. But when we are using array, this log n time can be reduced to constant time, which is much better. This approach is called top-down, as we can call the function with a query value and the calculation starts going from top queried value down to the bottom. Base cases of recursion and makes shortcuts via memoization on the way. Makes shortcuts via memoization on the way. This approach is called top-down. Yeah, that's cool. Bottom-up dynamic programming. When we start iterating from bottom to the up. Yeah, that is cool. If I want to find value for n, if yeah, initialize. This is iteration. This is iteration. This is the second solution that we have here. This thing. We have a for loop, a vector, storing state, and base case initialization. The same thing is here. Storing states in this thing, initialization of the base cases, and a loop going through everything. And now, of course, as written, this is a bit silly for two reasons. Firstly, we do repeat work if you call the function more than once. Wait, this is stupid. See, this is silly. Why? Of course, as written, this is a bit silly for two reasons. Firstly, we do repeated work if we call the function more than once. Makes sense. Makes sense if we are calling the function more than once. That makes sense. Secondly, we only need to use the previous two states to calculate the current element. Therefore, we can reduce our memory from this to constant. That also makes, but you cannot have it both ways, right? Yep. Either you store the state using O of n time, O of n memory, and you fill this array, or yeah, you have to fill this array, and then whenever you call this function twice or maybe multiple times, then you do not have to like go through this loop again. Or you could not store this, you could free your memory, make it constant in memory, but then you would have to go through this for loop again for every function call. An example of a bottom-up dynamic programming solution for Fibonacci constant memory would be this. So you are still storing memory. Max save is 3. Okay, max save is 3. Fib of I remainder max save, it is going to be 2. Okay, it will keep wrapping up. That makes sense. I minus 1 remainder max save, I minus 2 remainder max save. Yep. Here you have saved your memory, but you will have to go through the loop again and again for every function call. That is what we call eternal recurrence. Note that we have changed the constant from max n to max save. This is because the total number of elements we need to access is only 3. Yes, it is no longer, it no longer scales with the size of input and is defined by O of constant memory. Additionally, we use a common trick using the modulo operator, only maintaining the values we need. Yep, that is a trick. That is actually a trick. Yep, shit, that is cool. That is modular arithmetics. Your I will keep looping over. between 0, 1 and 2 because max save is 3 and you are doing modular arithmetic with max save as your base. Cool. Only maintaining values we need, that's it. That's the basics of dynamic programming. Don't repeat the work you have done before. One of the tricks to getting better at dynamic programming is to study some of the classic problems. These are the classic problems. Knapsack, and okay, rod cutting. Yes, edit distance. We have done rod cutting. We have done edit distance. We have done longest. No, we haven't done this one. We haven't done this one. This one is hard actually. Longest increasing subsequence. We did this. We did this in one of the code forces contest. Yeah, in one of the code forces problem. And subset sum. Okay, knapsack, we know 0 1 means either you choose a number, choose a element, or you not, or you don't. That is the 0 1 in 0 1 knapsack, and the other variant is 0 infinity, whether you don't choose a particular element or you can choose it any number of times. So that is 0 infinity knapsack. Given W, N, and N items with weights Wi and values Vi, what is the maximum value for each subset of item of size 1 to k when while assuring this thing is lower than the weight? Yeah, yep. Subset sum given n integers and t determine whether there exists a subset of the given set whose elements sum up to 9 to t. That is doable. That is very doable. That is very similar to what we read here in this. Yep, this is very similar to this. Yep, we can just call our function. Yeah, these two are similar. Actually, the same problem. Longest increasing subsequence, which we can do. Yep, which we can do, and this is going to take n square time, which is bad, but we can do it better if we maintain a priority queue, I guess. Counting paths in a 2D array. Given n and m, count all possible distinct paths from top left to top down, where each step is either from this. There should be a formula for this thing. There should actually be a formula for this thing. This is counting number of paths. This problem, counting number of paths, was here in complete search section of this book. Yep, right here. And there were 4 optimizations. Basic algorithm for pruning the search. Yeah, pruning here means when we know a solution is not going to work, then we eliminate that branch, that particular branch. We do not pursue it any further. That is called pruning, saving computation. That is cool. Longest palindrome sequence. Finding the longest palindromic subsequence, LPS, of a given string. Well, shit. This is more complicated than finding the longest increasing subsequence, LIS. Because in LIS, I only have to consider the thing on the left, but here, longest palindromic sequence, I have to consider the things on the left and the things on the right. Rod cutting is cool. Edit distance, we have written from programs for these two. And by the end, maybe in a week, we would be able to solve all of these problems without any difficulty. That would be cool. Related problems, bit mask dynamic programming, and of course the most important trick is to practice. Yep, dynamic programming on trees and digit dynamic programming. Bit mask. Let's see, is it there? Algebra, bit, numerical methods, integration, geometry, graphs. Inside graphs, do we have dynamic programming? On trees. Yeah. Let's do a few questions. Lead code. This one is a easy question, it seems. Cool. Shit. Support, creator. Yeah, this one is a very easy question. In lead code, Fibonacci TN is defined as the sum of the last 3 digits. That is cool. Yep. 0 is 0, 1 is 1, is 1. Okay, and since I know that my function is going to be called only once, then I can say int max size is 4 to find answer for a particular value. That is how many things I need. And nums size is max size, and inside we can do some initialization. Nums 0 equals 0, nums 1 equals 1, and nums 2 equals 2. And yep, now we can start iterating through our loop. For int I equals 3, will I less than equal to n I plus plus at any point, we will have nums I remainder max size will be equal to the sum of the last 3, which is nums I minus 1 modulus with max size plus, and there is a mistake, if this is s, go to the end. Yep, nums bracket I minus 2 modulus max size plus nums bracket I minus 3 modulus max, the spelling of max is wrong, max size. This should be cool, and at the end return nums n remainder max size. Let's see. Max size int non-stat. Okay, still invalid use of non-static data member. Max size. Let's say 0, 1, 1, and 0. Let's see. I can avoid this. Like a rebound cannot be deduced from a default. Bound cannot be deduced from a default member initializer. Okay, this is some C++ specific error. A rebound cannot be deduced from a default member initialization. Okay, then let me tell you the array bound. It is 4 or more. Specifically, it is max size. But now you will see that it is wrong misuse of max size. So let's go with vector of integers. Is that fine? Apparently not. Yeah, spelling is messed up at some places. Nums max size -1 max size nums max size nums I max size. Yeah, cool. Hmm, Es funktioniert. Yeah, cool, fine. On to the next one. Pascal's triangle. That is cool. It says easy. Okay. In Pascal's triangle, each number is the sum of the two numbers above it as shown here. Okay. Output. In the output, I have to output the whole thing. Okay. I will have a vector of integers called res number of row. That is going to be the size. And what is going to be my initial data? My initial data is going to be, or let me also give vector int. Yeah, default constructor. Right. Res of one. Res of 0. N is not, yeah, n is not going to be 0. So that is cool. Res of 0, that is my default. 0 dot push back 1. So now I have this thing ready, the top tile. And now I can start iterating for int I equals 1, I less than num rows, yes, and I plus plus. Now I need to reinitialize this thing, the vector here, which is res I dot assign what is going to be the size of this thing. If I am at ith row, what is going to be the size of that row? I am increasing by 1. So I1, I plus 1, I plus 1. At the first row, the size is 1, and the second row, size is 2, and third row, size is 3, then 4, then 5. Cool. I plus 1, and default value is 1. Now I will start iterating internally for int j will start at index 1, and j will go, since there are I plus 1, will lower the fourth row I equals to 3, and I can start iterating from 0, 1, 2, lower than I and j plus plus. The value here is going to be res ith row jth column, yes, that is the size. It is going to be equal to the sum of the above two, and the above two, the one on the left and on the right, are res I plus 1, that is the above row, and the one on the left is j minus 1, j minus 1, and j minus 1 plus res I minus 1 j. And is that correct? When j is 1, I add 0 and 1. When j is 2, I add 1 and 2. When j is 3, I add 2 and 3. So that is cool. And at the end, I can simply return my response. And let's see if that works or maybe not. Okay. Num rows declared here. Num rows. Okay, I messed up the spelling. Nums rows. Okay, nums rows is nothing. Num rows and anything else. No, seems to be fine. Pushback 1. That is my initial state. Cool. Yep, that is cool. That is fine. We can move on. Lead code 1025. Shit, I did this. I did this. Shit, yes. Shit, I did this question yesterday. Yesterday or maybe day before yesterday. Today is 25th. I did this on 23rd. Shit, I did this. I saw the solution for this problem on Reddit, and this is so cool. This actually feels like cheating. Look at this. Look at this. This feels like cheating. This is the whole question. This is my answer. Return not odd. That somehow works. And why is this a dynamic programming question? This just works. Somehow this works. That is cheating. Submit this and look at this. This is of course going to be the best solution. Look at this. This is very, very fast. And people are submitting this long code. They are actually using dynamic programming, dp of n, dp of 1 equals false, vector initializing stuff. That is cool. Okay, actually, like, what are they actually doing? They are creating a vector of Boolean values called dp of size n plus 1. So they will, I guess, start iterating from 0th till n, and who wins at n. And they know base case, and when there is 1, then false. That is, false would be returned when who wins? Alice wins or Bob? Return true if and only if Alice wins the game, assuming both players play optimally. If a player cannot make a move, they lose the game. And for 1, Alice won't be able to make a move. That is true. For 2, Alice can make a move. She can choose 1, and Bob will lose. And the rules are this. Given a number n, someone can choose any number from 0 to n, and this is the range is non-inclusive. You cannot choose 0 and n. You have to choose some number in between. So therefore, when n equals 1, you cannot choose any number because 0 and 1, there is no number, no integer between 0 and 1. And the number that you choose has to be a divisor of n. Replace the number of n, and yeah, then you can replace n with n minus x. And that is the thing. You have to keep doing this till one player cannot make a move any longer. So you do this. When n is 1, Alice will fall. Alice will fail. She will lose. Then you have 2 loops. This is n square. Start iterating for x represents this index, and then our internal loop going from when till that thing. By default, everything is false right here. And if remainder of I, shit, okay, equals false, then true. Since Alice is making the first move. Yep. If I can choose I and dp of I equals false, that is Alice would be winning there, then this guy wins here. Okay. No, then Alice wins here. If the person choosing that thing loses. That makes sense. That makes sense. This goes on from smallest to biggest. And if this thing is ever true, it is going to be true. Yeah. So this is basically taking OR of the thing. Cool. Cool. That is one solution to this thing. Code forces vacations. Shit. Is this the problem that I struggled with? No. It is a 1400 problem. Is this in CP31? Vacations. This could be at CP31. Nope. It doesn't seem to be. There is no vacations here at 1400 level. Nope. That is fine. And it has been 3 hours, which is fine. And we can continue with our reading of the CP algorithms article. And what have we discovered till now on this stream? We have written some functions. We went through competitive programmers handbook, dynamic programming, whole chapter. We did this whole chapter. So that is good. We did this whole thing. We did half of this yesterday and remaining half today. And yep, we wrote function for this. Yep, we wrote a function for this edit distance. And after this, we went and we solved some CSCS dynamic programming questions. 3, we were able to solve 3, and we were getting time limit exceeded error in the next one somehow. So we have to make our thing even more effective than it is. And yeah, we did that, and then we went on and we read an article on dynamic programming in here. Dynamic programming, introduction to dynamic programming. This is what we read. And the next one is knapsack, actually. Knapsack, that is cool. So now what we have to do in dynamic programming, read this knapsack thing, knapsack article, solve the problems one by one, and then go on to this thing, read this, solve these problems, then read about DP optimization, and basically complete this whole dynamic programming section of this thing, of this website, and solve a bunch of these problems, then solve a bunch of dynamic programming problems here. And I also have the CLR RS book, which I won't be reading on a stream. Yeah, I will be doing this on back end of a stream offline. So yeah, this is cool. In 1 week, we would be really good at dynamic programming. That is the goal. And tomorrow is a contest, which is going to be fun. And for now, that is going to be the end of today's stream. It has been 3 hours and 4 minutes, which is a very long time if you are studying something. And thank you for being here. Bye.